So we're going to be taking a look at what's called the dot product, okay? We've already looked at some operations with geometric and algebraic vectors, adding, subtracting, and we multiplied a vector by a scalar, okay? Well, today we're going to be taking a look at the first way that we're going to multiply two vectors together, okay? So this is the product of two vectors. This one is called the dot product, all right? And with the dot product, we are going to be using basically a dot in between the two vectors. So whenever you see that dot, right, you just use whatever vector you have. We put a dot in between. We're going to use something specific. We mean something specific here. All right. So just as it reads out here, the definition of the dot product, okay, is going to be the magnitude of each vector. We're going to take the product of each vector, all right, the magnitude of them, and then we're going to multiply by the cos of the angle between the two vectors, all right? So in the case that I've already got printed out here, we've got the two vectors A and B, all right? They're lined up tail to tail. This is what they have to be. So when two vectors are lined up tail to tail, all right, we look at the smallest angle between them. It's got to be between 0 and 180 degrees. Okay. Now, the two vectors themselves are non-zero. Okay, so we don't get a zero vector. All right, at the end. All right. And one thing to notice on this one is that by the definition of this dot product, since both magnitudes are just scalar quantities and the cos of theta is a scalar quantity, we end up with the dot product being a scalar itself. So it's also called the scalar product. All right. So if you see that in the textbook or whatnot, calculating the scalar product, this is what they're referring to, the dot product itself. Okay. So as a quick example, let's take a couple of ideas here. For example, if we have, let's say we've got the magnitude of one vector maybe of length 4. Let's say we've got another vector whose magnitude is 7, and the angle between them happens to be something like 47 degrees. All right. Well, let's calculate the dot product, okay, of those. So you've got the product of the magnitudes times the cos theta, the angle between them. So 4 times 7 times the cos of 47 degrees. All right. So you throw that in your calculator, 4 times 7 times the cos of 47 degrees, and you get this answer approximately 19.1. Okay. So that's what we have there. Okay. So do that. Now, let's say example B, we're going to do a couple of those. Let's say we have the same A and B, okay, but the angle between them, these are perpendicular vectors, okay? The angle between them is 90 degrees. But when we take a look at the dot product, all right, again, we have the 4 times 7, but in this case, we have cos of 90 degrees. Well, we all should know by this time the cos of 90 degrees is 0, so that means the dot product is 0. All right, so one thing to keep clear in our heads right here, perpendicular vectors give us the dot product of 0. Okay, if we have a dot product of 0, the vectors are perpendicular. All right, the last thing I want to do is, again, the same vectors A and B, same magnitudes. However, in this case, we're going to go past 90 degrees, and we're going to say that we've got an angle between them of, let's say, 115 degrees. All right, so calculate the dot product here again. The 4 times the 7, cos of 115 degrees there. So you've got your 28 times the cos of 115. You end up with a negative number, okay, approximately negative 11.8. All right, so here are a couple of things to take a look at. I've given you one example of each case that you're going to get. If the angle is between 0 and 90 degrees. Sorry, between, take off those 1 second. All right. Then the dot product is going to be positive, right? If the angle between them is 90 degrees, if they are perpendicular vectors, then the dot product is going to be equal to 0. And finally, we see that if the angle is greater than, in fact, let me just tighten that up a little bit. If we know that it's between the 90 and 180 degrees, then we know that the dot product itself is going to be a negative number. Okay, so that's just a couple of, ideas behind it, principles behind the dot product. Okay, one of the applications, okay, of the dot product, one of the main applications is this concept called work. All right, work is the dot product between the vector force and displacement. Okay, so we're going to say work. I'll put down here, this is force, this is displacement. Okay, and it's how much work you do basically in the direction of the movement in the displacement itself, right? So if we were just to make up a quick little example of work, we can say, we're going to calculate the work done if, actually I'll put if down instead of on, the work done if you exert somewhere in there, I think, whatever, exert, let's just call it a 90 Newton force, 90 Newton force at an angle of, we'll go just 10 degrees. All right, so basically what I'm saying on this one, I know you can't see me here, but if you're going to push something across a floor, you're going to, in a lot of cases, give a little bit of a lift to the object, okay, as you move it, okay? It takes off a little, takes off that friction, right? And so it's a little bit easier to move it, but you've got that upward force a little bit to it, okay? In some cases, you're straight across, but that's the boring case. So we're going to say the angle of 10 degrees for, we'll just say that it's 5 meters. Okay, you're pushing something across the floor. All right. So here's the thing. So you're going 5 meters. We can go 5 meters to the right, 5 meters to the left, or whatever, in your forward direction to make sure that the 5 meters is the displacement, right? Okay. So again, what you do is you have, what is the work done? So we know it's the magnitudes, product of the magnitudes times the cos of the degree between them. And so you simply have the 90 newtons times the 5 meters times the cos of 10. You have 90 times 5 times the cos of 10, and you end up with approximately 443.16 Newton meters, okay, or joules. All right, that's the unit of work. Okay, so that's just the idea, okay, of the application that you can have between them. All right, between or using the dot product. Okay, so this is all. All right, let me go back up in here. All right, what we said was this is the geometric way of calculating the dot product. Notice that we have it set up with our directed line segments lined up tail to tail. We look at the smallest angle between them, between 0 and 180 degrees. Okay, and we're all set. All right, so let's now take a look at how we calculate our algebraic dot product. Algebraic dot product. Okay? So the algebraic dot product, let's take a look at what we've got so far. So we've got, let's say we're given any old vector, A, where we use the algebraic components, A1, A2. All right. We've got B is B1, B2. And the vector C, okay, which is defined to be A minus B. Okay, we're going to use that defined, so then we're going to say that that's A1 minus B1 and A2 minus B2. Okay, so that's our definition of what we have there. All right, so we can say with some confidence here that the magnitude of A, okay, actually the magnitude squared, let's say, is, well, let me go back a little further. I can already think of this in my head, but let's go. The magnitude we know is the square root of A1 squared plus A2 squared, right? So then if we square the magnitude, we square the right-hand side, and we're just left with A1 squared plus A2 squared, okay? Similarly, we can say that the magnitude of B squared is equal to B1 squared plus B2 squared, right? And if we then go to C, the magnitude of C squared, all right, would then be A1 minus B1 squared plus A2 minus B2 squared. Okay, so make sure you understand that. If you need to pause and go through it yourself, make sure you have that, okay, before we move on. So there's one thing right there that we know that we have, all right? So therefore, this means that C, the magnitude of C squared, get rid of that little dot, which is not the negative, okay, of C squared, if we expand this right-hand side, then we have A1 squared minus 2A1B1 plus B1 squared plus, expand the next bracket, A2 squared minus 2A2B2 plus B2 squared. Okay? Now, next thing we want to do, let's take a look, and what I'll do is I'll just do some highlighting here. A1 squared plus A2 squared. Notice that that is the magnitude of A1, or A, right? So that's the magnitude of A squared, okay? The other thing that we can look at, I'll use a different color here, B1 squared plus B2 squared. Notice that that is the magnitude of B squared. So plus the magnitude of B squared. And then we're left with, for now, this oddball looking thing of the negative 2 times A1B1 minus 2A2B2. Okay? So what we could do, we'll just put this aside and call this our equation 1. All right, we'll leave that aside. We're going to say also from cosine law, all right, and the reason why we're using the cosine law is if you take a look at what we designed up here, we've got our A and B, okay, with the angle between them, and C is A minus B, okay, and this is what this is set up here, so our C is right there. So if we're just looking at the magnitudes here of each, we can use the cosine law directly, okay? So from the cosine law, we know that the magnitude of c squared is equal to the magnitude of a squared plus the magnitude of b squared minus 2 magnitude of a, magnitude of b, cos of the angle between them. And so here is our second equation. All right. If we're looking at equation 1, you can see that we have an expression for the magnitude of c squared. This is it. And in equation 2, we also have another expression for c squared, right? And that's this one. So we can relate these two together, right? So we can say from equation 1 equaling equation 2, right? We get the a squared, the magnitude of a squared plus the magnitude of b squared minus 2a1b1 minus 2a2b2 is equal to the magnitude of a squared plus the magnitude of b squared minus 2 times the magnitude of a times the magnitude of b times the cos theta. All right. Now, looking at this as an equation, we can see that the magnitude of a squared reduces out because there's one on either side. The magnitude of b squared, again, reduces out because there's one of those on each side. And we are left with this negative 2a1b1 minus 2a2b2 is equal to negative 2 times the magnitudes, product of the magnitudes, cos theta. And when we reduce the negative 2, we divide everything by negative 2. We can see that a1, b1 plus a2, b2 is equal to the magnitudes times cos theta. And so what is the right-hand side? Well, the right-hand side is, by definition, the dot product. So we now have our very simple equation for the algebraic dot product. You just have the sum of the product of the corresponding components. So this is key. This is the algebraic dot product right here. So make sure you make note of this. All right. When we do examples, they're very, very straightforward. Okay, but there's something really key that we can take a look at with this example or with these examples. Okay. So what we're going to do is we're going to, in the following, we're going to calculate the dot product and here's the key, and determine the angle between the vectors. Okay? This is going to be a key one. We are going to be using this a lot. Whenever you need to find the angle between two vectors, all right, from now until further notice, you use the dot product. Use the dot product. We'll get into that, okay? So we'll just take a look at two examples so we can get a handle on this, and then we'll be done. All right. So let's say, for example, our first is 1, negative 3. Our second is, let's say, 4, 7. Okay. Our second one, let's say we have an angle, or sorry, a vector of negative 3, 5. And we'll take a look at 4, 2. Okay, something like that. We'll take a look and see what we've got. So first of all, the dot product. Okay, so very simply, the dot product between these is you multiply the components together. So 1 times 4 is 4. You add that with the product of the y components, which is negative 21. And you end up with negative 17. Okay, very quick and easy on this one, right? Easy way of doing the dot product. You get the work too if you have the components. Then with the other one, all right, let's take a look. A dot B, multiply that out, you get negative 12. Add that to the 10, because you're multiplying the 5 times the 2, you get a negative 2. we already know in both cases here that the angle is going to be greater than 90 degrees. It has to be from one of the products that we, or one of the properties that we looked at before. But here's what we do. When we take a look at finding the angle and we use the dot product, we use the definition of the dot product. There's the angle right there in cos theta, right? So when we rearrange our equation, we have that cos theta is equal to the dot product divided by the product of the magnitudes. Okay, and then we can just use the inverse of cos to find out what the angle actually is. So we've already calculated the dot product in this case, which is negative 17. The magnitude you can see is here is the square root of the 1 squared plus 3 squared. I believe that that's the square root of 10, right? And so theta, which is the cos inverse of negative 17 over, oh wait, did I do, yeah, I did do that. Negative 10, that's for the a, or the square root of 10. We also have the square root of, for the b vector. So 4 squared is 16, 7 squared is 49. So that would be a 65. Okay, you have to do the magnitude of a times magnitude of b, right? Okay, so here's what we have here, 65. And then we can put this all in our calculator, and I recommend that everybody do this so that you get practice, right? Practice. So negative 17 divided by, we need the square root of 10 times the square root of 65. I get approximately 131.8 degrees. Notice again, greater than 90 degrees. Okay, an obtuse angle. Let's do it again. Make sure we understand it. Okay, where it comes from here, we've got the dot product, or we know we can use the cos theta. We're trying to find the angle. We know when we rearrange the dot product, magnitude of A times magnitude of B underneath here. We already have the dot product of negative 2. We now find the magnitude of A. Okay, so 3 squared is 9, 5 squared is 25. Add those together, you get the square root of 34. Now you get B squared, or sorry, the magnitude of B. 4 squared is 16. 2 squared is 4, so that's the square root of 20. So therefore, when we use the cos inverse, negative 2 over square root of 34 times the square root of 20. Make sure you put this in your calculator correctly, right? We're doing the cos inverse of negative 2 divided by, we have the square root of 34 times the square root of 20. And I get approximately 94.4 degrees. Okay. Now, if you're not getting that, it's one of two things. First of all, you got to check your calculator to make sure that you're in degrees and not in radians or gradians. The other thing is you want to make sure that you're inputting your numbers in correctly. You have to tell the calculator that you are dividing this product. Okay? What I do is when I use a bunch of brackets in my calculator, I actually put in the cos inverse. I have a bracket, it's negative 2, all right? And then I do the divide by, and I put another bracket in here. And I say it's the square root of 34 times the square root of 20. And then I end my bracket, another bracket, right? And then press equals, okay? So try that, make sure you get the right answer on there. Work yourself through those, okay? As I put on here, it is key. Make sure that whenever you're asked for the angle between the two vectors, you're now going to use the dot product. That's how we find it, okay? All right, that's it for now. You can try your hand at these questions here.